Okay, we need to prove a lemma before we see the next theorem. Let the set A be an arbitrary union of subsets, and let the set B be an arbitrary union of subsets. Then the complement of A and B is a subset of the arbitrary union of the complements. All right, so let the point X be in the complement of A and B, and this is the complement of the union of the subsets B sub I, or correction, the union of the subsets A sub I in the union of the subsets B sub I. And as this point X is in this complement, then the point X is in the union of the sets B sub I and is not in the union of the sets A sub I. So as the point X is not in the union of the point or of the sets A sub I, then that point X is not in any of the sets A sub I. So it is not in the set A sub I for any index I. And so it must be in the complement of the set A sub I in some larger space X. And this must be true for every index I. Now, as the point X is in the union of the sets B sub I, then there exists at least one index I such that the point X is in the set B sub I. So there exists at least one index I that the point X is in the set B sub I, and for every index I, it is in the complement of the set A sub I in a larger set X. And so there exists at least one index I and I such that the point X is in both the set B sub I and the complement of the set A sub I. Since the intersection of B sub I with the complement of A sub I is the complement of A sub I in the set B sub I, we have that the point X is in this complement. And as it is in this complement for at least one index I, it is in the union of those complements. And hence the complement of A and B is a subset of the union of the complements. All right. So now we're ready to look at the theorem, and this is perhaps one of the most important theorems in measure theory. Let the set X with some sigma algebra script m and some measure mu be a measure space let the set script m star be the collection of subsets E in the space X for which there exists sets A and B in the sigma algebra script m such that A is a subset of E, which is a subset of the set B, and the measure of the complement of A and B is empty, or not empty, but is 0. And in this case, we're going to define the measure of the set E to be the measure of the subset A. Then the collection scriptum star is a sigma algebra, in the space X, and the function mu, which we have now extended, is a measure on the sigma algebra scriptum star. All right? So we'll prove that the collection scriptum R is a sigma algebra by definition. So first, notice that for every set M in the sigma algebra scriptum, it is certainly a subset of itself and a superset of itself, and the measure of the complement of the set in itself is the measure of the empty set, which we know to be 0. And so the sigma algebra M, script M, is a subset of the collection of sets script M star. So as the set X, the entire set X, is in the sigma algebra script M, it is also in the collection script M star. So the collection script M star does contain the entire set X. Okay, second, let the set E be an element in the set script M star. Then there exists sets A and B in the sigma algebra script M such that A is a subset of E, which is a subset of B, and the measure of the complement of A and B is 0. And so the complement of each of these sets in X is also a chain. X set minus B is a subset of X set minus E, which is a subset of X set minus A, where the complement of A and the complement of B are in the sigma algebra script M, and the measure of the complement of A set minus the complement of B is the measure of the complement of A with the intersection of the complement of B, which is B. And so this is the measure of B set minus A, which we know is 0. And so if the set E is in the collection script M, then we have that its complement is in the collection script M star. So again, if the set E is in the collection script M star, then its complement is also in the collection script M star. All right. So next, let the collection of sets E sub I be a countable collection of subsets or of sets in the collection script M star. Then there exists collections of sets A sub I and B sub I in the original sigma algebra, script M, such that A sub I is a subset of E sub I, which is a subset of B sub I, and the measure of the complement of A sub I in B sub I for each of these chains is 0. So let the set A be the countable union of the sets A sub I. Let E be the countable union of the sets E sub I. And let B be the countable union of the sets B sub I. Then A is a subset of E, which is a subset of B, where A and B as countable unions of subsets in the sigma algebra script M. Their countable union is also in the sigma algebra. So now we need to show that the measure of the complement of A and B is 0. And so since the complement of A and B is a subset of the countable union of complements A sub I and B sub I, we have that the measure of the complement of A and B is less than or equal to the measure of this union Now, as we cannot guarantee that each of these complements as a set is mutually disjoint with another, the best that we can say is that that the measure of this union is less than or equal to the sum, the countable sum, of the individual measures of those sets. But each of these, the measure of each of these sets is 0, and so the sum is 0. So that is enough to establish that the measure of the complement of A and B is 0. And so if the set script M contains a countable collection of sets, then the countable union of those sets is also in the collection script M star. So script M star is a sigma algebra by definition. All right. So now we need to show that the function mu is a measure on the sigma algebra script M star. And as the measure is defined to be the measure of a set E in the collection script M star is defined to be the measure of a subset that is contained in the original sigma algebra script M, and mu is a measure on that algebra. Clearly, mu is a countably additive function, so we need only show that mu is well defined on script M star. So suppose that E is a subset of A, which is a subset of, or rather E is a superset of A and a subset of B, And let's suppose that this is true for another pair, that E is also a subset of A sub 1, or a superset of A sub 1 and a subset of B sub 1, and that it is true that the measure of B set minus A is equal to the measure of B sub 1 set minus A sub 1, which is 0. Then the way that we define mu is that mu of E, the measure of E, is equal to the measure of A, as A is a subset of E, and mu of E, the measure of E, is equal to the measure of A sub 1, since it too is a subset that satisfies the condition. So we need to show that these are the same value, that is, that mu of A, or the measure of A, is equal to the measure of A sub 1. So, as the set A is a subset of the set E, and the set E is itself a subset of B sub 1, we have that set A is a subset of the set B sub 1. And so, if we now take the intersection with the same set on both sides, A intersect the complement of A sub 1, then this is a subset of set B intersected with this same set, the complement of A sub 1. But this is the complement of A sub 1 in A, the set A, which is a subset of the complement of A sub 1 in the set B sub 1. So, as this is a subset of this set, the measure of this set is less than or equal to this set. So the measure of the complement of A sub 1 in the set A is less than or equal to the measure of the complement of A sub 1 in the set B sub 1, which we know to be 0. And so the measure of A set minus A sub 1 is 0. Now notice that the set A can be expressed as the union of the complement of A sub 1 in the set A with the set A sub 1, where A set minus A sub 1 intersected with A sub 1 is empty, because this set is the complement of A sub 1, and so they must be disjoint. And so we can apply the countable additivity. So mu of A is mu of the union of the complement of A sub 1 in A with the set A sub 1. And so this is the sum of the measures, A set minus A sub 1 plus the measure of A sub 1. But the measure of the complement of A sub 1 in A is 0. So we have that the measure of A is equal to the measure of A sub 1. So in other words, the countably additive function mu assigns to the set E a unique value, or a single value, and so it is well defined on the collection script M. Okay, so that completes the proof. Now the extended function mu that was just defined in the theorem is called the completion of the measure space to mu, and the sigma algebra script M star is called the mu completion of the original sigma algebra script M. And what do we mean by completion? A measure mu on a sigma algebra script M is complete if every subset of a set of measure 0 is measurable. And so the previous theorem tells us that given a measure space, the measure can be made complete by the method that we used in the theorem.